Hi, this is Dr. Vikas Paul. In this session, we are going to discuss about a problem on fixed beam with 2-point loads. A fixed beam of length L carries 2-point loads in the position as shown in the figure. Find the final moments at C and D when beam is simply supported, and draw the resultant bending moment diagram. So you can see 2-point loads here. The span is also shown here. So first of all, we need to find the moments. So here MA is equal to MA1 plus MA2, MB equal to MB1 plus MB2. MA1 is a fixed end moment due to first load W at C. So you can see the figure here, W, only one load we have shown here. So MA1, MB2. So if you see the formula, we have a formula for eccentric point load A and B distances. The moments are WAB square by L square MA, and MB is WA square B by L square. The same formula we can apply here. Here A is L by 3, B is 2L by 3. So if we substitute, we can find MA1 and MB1. MA1 we will get as minus 4L by 27, MB1 minus 2WL by 27. So similarly, let MA2 and MB2 be the fixed moments due to second load W at D. So second load W at D is shown in this figure. So MA2, MB2 we can calculate using the same formula. Here A is 2L by 3, B is L by 3. So if we can get MA2 equal to minus 2WL by 27, MB2 equal to minus 4WL by 27. So why minus here? So you can see here minus WAB square by L square MA. Minus because at the fixed ends, we know that at the fixed end supports, it is a negative bending moment. It is hogging. Therefore, minus WAB square by L square minus WA square B by L square. So we will get MA2 as minus 2WL by 27, MB2 as minus 4WL by 27. So MA equal to MA1 plus MA2. Therefore, if we add it, minus 4WL by 27 minus 2WL by 27 we will get as minus 2WL by 9. So MB equal to MB1 plus MB2 we will get minus 2WL by 9. So this is a bending moment diagram for fixed end moments. You can see here a rectangle with 2WL by 9, 2WL by 9 at A and at B. Now we need to draw bending moment diagram. So we know the procedure how to draw the bending moment diagram. First of all, we will calculate the reactions. So we will remove the fixed end supports and we will put simple supports. And for this, we need to draw the bending moment diagram. So first of all, calculate RA and RB. We know how to calculate RA and RB using sigma Fy equal to 0 and sigma MB equal to 0. So and bending moment diagram. So after calculating RA, RB, we will get RA equal to W equal to RB. So we can calculate bending moment values. We know the procedure how to calculate bending moment values. So after calculating bending moment at A, C, D and at B, draw the bending moment diagram. So in this bending moment diagram for simply supported case, you emerge that previous bending moment diagram for fixed end moment we have calculated now 2W by 9. So that one we have to emerge here, and this as it is negative. So in the net bending moment diagram, you show here negative minus and plus upwards minus here as shown in the figure. This is a final bending moment diagram. Let us see another problem on this fixed beam combination of loads, that is UDL and point load. So in this case, we need to calculate the fixed end moments, reactions and deflection at center, and we should draw shear force and bending moment diagram. So first of all, in the same way we can calculate MA and MB final end moments. MA equal to MA1 plus MA2, MB2, and MA. So MA equal to MA1 plus MA2, MB equal to MB1 plus MB2. So here, first of all, we'll consider the UDL only on the beam, fixed beam, and for this case, we'll calculate MA1 and MB1. So MA1 formula for half UDL, when there is a UDL on half of the span for the fixed beam, we know that formula is minus 11 WL square by 192. Why minus here? Because there is a negative bending moment hogging at the fixed supports. So here W is 40, therefore minus 11 into 40 into 8 square by 192, it is minus 146.6. So MB1 formula is minus 5 WL square by 192, minus 5 into 48 square by 192, it is minus 66.66. Similarly, if we take point load 80 kN separately and calculate MA2, mb2. We know the formulas: minus WAB square by L square minus WA square B by L square. So in the here A is 6 meter, B is 2 meter. So in that way we can calculate MA2 minus 30 MB2 minus 70. So add it. MA equal to MA1 plus MA2 minus 146.6 minus 30 you will get minus 170, and MB equal to MB1 plus MB2 you will get minus 156.6. Now we need to calculate the reactions. Remove the fixed supports and put the simple supports and calculate RA RB using sigma Fy equal to 0 and sigma moment about B equal to 0. So you will get RB as 97.5 and RA as 142.5. So now we need to draw the shear force diagram. So we know how to calculate the shear force values. So we can calculate shear force at A, B, C and at D, and the shear force diagram will be as shown in the figure. As it is UDL, from A to B it is you can see the shape there, and in BMD from A to B it is a parabola. It is a parabola from A to B, and from B to C and C to D is a straight line. So for simply supported beam, first we have to draw the bending moment diagram as we got the values here for MA, MB, MC and MD, and then we should emerge the final end moments which we have calculated previously. So MA, MB already we have calculated now, that we have to show here. So net bending moment diagram we can show here. Now we need to calculate the deflection, right? So EI is given in the question. So using Macaulay's method we can calculate the deflections. So we need to take a section in Macaulay's method. So I have taken a section XX in span A on the UDL. Then from at a distance of X from D. So mxx equal to rb into x minus 8 into x minus 2 minus 14 into x minus 4. So here in this way we can equate mxx equal to EA d square by dx square. So we know the Macaulay's method procedure. According to that, if we follow equating this both of this, we can find the we can get an equation 1. So integrating it we will get in terms of dy by dx, and plus c1 we will use a boundary condition x equal to 0, theta equal to 0, dy by dx equal to 0. We can find a c1 value, it is 0. So substituting c1 value again, we will get slope equation. Again integrating we will get c2, and applying x equal to 0, y equal to 0, we will get c2 equal to 0. Substituting c2 equal to 0 in the above equation, we will get a deflection equation. So to find the deflection at center, so substitute x equal to 4. So y center we can find. Substitute x equal to 4 in the deflection equation, we can find y center equal to 0.1453 mm. Right.